Welcome from my side for today's webinar on the ColorVis 705 IQ color sensor. My name is Nicolas Kaltwasser. I'm application engineer at Xylem Analytics for about 2 years now. And I'm supporting product management and sales with creating technical content for educational reasons. And with me today is Patrick.
Yeah, welcome also from my side to this training here on the color sensors. I'm Patrick, I'm product manager in Xylem Analytics Germany for now 12 years, and my responsibility is in the process segment, and I take care on all the products for continuous water quality monitoring. Thanks for joining.
Okay, with that, I think we can start. So for today, we want to talk about the ColorVis sensor, and before going to the product, we want to have a look at the application. So we're going to ask the question, why do we measure color and what for? What regulations, units, and standards do we have? And then secondly, we're going to look at the product. So Patrick is going to introduce the ColorVis IQ705 and shows us the specs and features. And then, as mentioned, at the end of the presentation, we will have time for a Q&A. So starting off with the application, let's step back for a second and just ask ourselves why color is an important parameter to measure. And we have to be aware that color is an indicator for the presence of dissolved organic matter, so DOM, of minerals and metals, industrial contaminants, and also algae. And that makes color a suitable monitoring parameter in all the 3 applications that you see here. So we can use color in wastewater, in drinking water, and in surface water. And now going deeper into wastewater, what is color used for? So there are a couple of things. The presence of DOM can consume coagulants, and that makes that increases the chemical requirement. So also high color is often related to more fine particles, which can cause faster fouling, shorter filter run times, and higher backwash frequency. And then also higher color reduces UV transmittance, making UV disinfection systems less effective. So we can see color is affecting the treatment process, which is why it is monitored in wastewater treatment plants, typically throughout the process and at the outlet. On the drinking water side, all these aspects also count. And then additionally, color is an indicator for changes in source water quality. We have to be aware that DOM reacts with chlorine to form regulated disinfection byproducts, and color can be an early warning here. And then also color helps identify corrosion in pipe networks, and it also affects public perception of water quality. And for these reasons, color is typically monitored at a drinking water plant inlet throughout the process, at the outlet, and also throughout the pipe network. And then on the surface water side, color signals algal blooms and also ecological decay processes. And also it affects public perception of water quality, which is why color can be monitored directly in rivers, lakes, streams, and other natural water bodies. Because color is such an important parameter, it is also mentioned in many regulations worldwide. And here are just some examples of regulations and where color is regulated. So we see in drinking water, the European Union is regulating color. We find color also here in Germany in our regulation. And I'm highlighting here the unit, which is meter to the power of -1. We will come to the units in a second, and this is quite interesting because we have two different units. Here is a snapshot from the Environmental Protection Agency in the United States. And they are also regulating color in drinking water, but they use a different unit. It's the so-called color unit or platinum cobalt unit. We find also regulations and limits in wastewater, here again in Germany, specifically for textile manufacturing and textile finishing industries. And it's using again the meter to the power of -1 unit. And then I also found a regulation in China. I'm not 100% sure if this is up to date, but you can see here for wastewater color is also limited in dyeing industry, for example. And here again, the unit is the platinum cobalt scale. So talking about the different measurement units, this slide will explain us what the differences are. So we saw that there are regulations that use the milligram per liter platinum cobalt scale, which is also called AFA or Hazen. And it measures simply the yellow tint of liquids by comparison with platinum cobalt reference standards. And you can see that here on the right, when you have 0 milligram per liter platinum cobalt, and it's basically colorless. And when you increase to 500 milligram per liter platinum cobalt, we get a very strongly yellowish color. So the second unit that we saw is the meter to the power of -1, which is familiar to us as the spectral absorbance coefficient unit. So for this unit, we're basically just measuring the absorption of light over a given path length and at a specific wavelength. And we do that with a photometric measurement. Another important aspect to keep in mind when we talk about color measurement is the difference between apparent color and true color. So apparent color is the color of the raw water sample, while true color is the color of the water sample freed from dissolved substances, meaning that we have to prepare our sample. And in laboratory, the typical approach is that we filter through a 0.45 micrometer membrane to remove the dissolved substances. And for online sensors, like our ColorVis sensor, we have an integrated turbidity compensation. So let's have a quick look at the measurement standards and methods. And it's important to highlight that there are standardized methods only for laboratory. And here they can be grouped into visual inspections, which is just comparing a sample to a standard with your bare eye. And then the other group of methods is using optical devices to perform spectrophotometric analysis. And the two main standards that we have are the ISO 7887 and the ISO 6271. And you can see here the 7887 is used for the measurement with the meter to the power of -1 scale, while the other one is using the Hazen scale. And then the 7887 is giving us recommendations for measurement wavelength, which are 410 nanometer, 436, 525, and 620 nanometer. On the other hand, the ISO 6271 for the Hazen measurement is not defining a certain wavelength to do the measurement at, But a typical wavelength is 455 nanometer, as this is the main absorption peak of the platinum cobalt solution. And so our ColorVis 705 IQ is guided by these standards methods. And Patrick will show you later on that we are covering all those wavelengths and even more with the sensor. So let's quickly summarize what we just learned. Color is a good parameter for trend monitoring of water quality, of pipe network integrity, and also treatment process efficiency. It is regulated in many parts of the world for drinking and wastewater. Also, online monitoring is guided by standard methods and is increasingly integrated in utilities. And then we also learned that monitoring spots in the process are for wastewater treatment throughout the process and at the outlet. In drinking water, it's at the inlet, throughout the process, at the outlet, and in the pipe network. And for surface waters, it can be anywhere just right in the water, like in rivers, lakes, and ponds. And with that, I'll pass it on to Patrick to introduce the ColorVis sensor.
Thanks, Nicholas. So let's have a look into the sensor itself that provides that parameter color. So basically, the so-called ColorVis 705 IQ sensor is very similar to our standard UV-VIS sensor, which you probably already know. These are the sensors with titanium shaft, PEEK material, sapphire glass. We have the integrated ultrasonic cleaning, and we have the option to add pressured air cleaning as well. And of course, these sensors are connectable to the IQ sensor net. So when we look especially on the ColorVis, when we have that now maybe for the installation and we connect it to the IQ sensor net, then the sensor will pop up as all sensors in the IQ sensor net automatically. And the default setting is that we see one single parameter at the display. And this parameter, which is shown, covers the wavelength 410 nanometers. This is the wavelength which we use according to the ISO method. And this parameter is also compensated with turbidity. So the turbidity compensation is active. That means for that wavelength, we are measuring the true color. When we look here in the specifications, which I have here on the slide, then you see on the right-hand side the available wavelengths in the sensor. And in the green cycle, it's the default setting. And on the left, you see the option for true or apparent color. So the default setting is true color. And if true color is set and active, then we can also use a factor for this true color, which is between 0.1 and 2, and the default setting is factor 1. So in fact, there is no turbidity compensation because the factor is just multiplied with 1. That's not a big change at the moment. Anyhow, of course, you can change this. So you can change the factor, you can deactivate the true color, which means deactivating turbidity compensation. And of course, you can choose in the sensor settings a different wavelength if you like. So on the next slide, I want to show you on the first line, the ColorVis. This is the one standard sensor to measure color. And you see on the very left, the order number. And on the right-hand side, you see the number of possible parameters you can show. So I mentioned the default setting is just one parameter, but you can show up to 3. This is very similar to other spectral sensors. You can go into the settings of the sensor, and there is a menu point which is called number of sensors. And in that case, it's number of color sensors. And then you can increase the number to 3. And if you do this, then you can show up to 3 parameters on your display. So, for example, when installing the sensor for the first time and the customer is not 100% sure which wavelength to use, or the customer is not 100% sure if he wants to do turbidity compensation or not, and if turbidity compensation, which factor to use. So that means in a test phase at the very beginning, you can choose 3 different parameters. You can choose whatever wavelength, and you could even choose the same wavelength 2 times. One is compensated and one is not compensated, or both are compensated but with different factors. So this allows you at the very beginning really to fit the sensor to the customer's needs, and therefore we can pop up to 3 parameters. After some testing phase, it's probably clear which wavelength or which compensation fits best to lab values, and then the customer can just go on with that one sensor which is chosen. In the other lines here, you see other sensors which provide color. So there is a ColorVis sensor providing carbon parameters, total suspended solids, and color. And there are also 2 UV-VIS sensors for nitrate, carbons, suspended solids, and color. And on the right-hand side, you see the possibility which sensors you can show on the display. So let's go through this in line order number 66, the WTW TS. That's the product number 3. A customer which purchases this sensor expects a nitrate parameter. So the N parameter is shown. The customer expects a carbon parameter. That's why he purchased a WTW. So a carbon parameter is shown. And the customer expects color and total suspended solids. So the standard setting is that from every of these parameter groups, nitrate, carbons, color, suspended solids, 1 parameter is shown. And as you probably know, these sensors can pop up to 5 at all. So the 5th parameter can then be selected out of the carbon range. We are unlikely not able to make this very dynamic. So we cannot switch off nitrate, we cannot switch off TS to get another parameter space for carbons or color. That is not doable in the current software. That is why from every parameter group, one location or 1 position is occupied anyway, and the 5th is then available for carbons only. That means when you have to test what I mentioned just a few minutes ago, when you want to test which wavelength or which compensation fits best for such testing phases, the ColorVis sensor is probably the better one because you have more options to choose color parameters. And when this decision is done, then you can stop the test and finally sell an WTW or ColorVis if the customer needs other parameters, because then you know which color is relevant. All right, on the next slide, I want to stress a bit on the competition. So the main competitors for spectral sensors in general are the known companies Ascan, Trias, a few local manufacturers for sure. Tatis and Hemera are also providing color sensors or analyzers. And the pain points of customers using these instruments are that they might need more parameters than just color. And some of these manufacturers are not providing that much parameters in their portfolio like we do. So we could have a match here that we provide something which others don't. Which also means they want to have an all-in-one solution. They want to have one system where all these parameters are measured. And well, some of these manufacturers, they have an instrument with a sensor there, but the color analyzer is a separate instrument, or maybe a TOC analyzer is a separate instrument. That is our benefit of the IQ SensorNet, to summarize that all in that one system. And of course, when customers already do have analyzers, for example, wet chemical analyzers, that's the nature of analyzers. They always require more maintenance than sensors. If they want to get rid of this, then a color sensor is maybe the option. Which means our value proposition to convince customers is we have multi-parameter sensors, so you can measure much more, not just color. These sensors are compatible to the IK SensorNet with all the sensors in our portfolio, and the color sensors don't need chemistry-like analyzers. So on the next slide, again, how we win, so to say. We have the all-in-one solution. The sensors require lesser maintenance than analyzers. We are compliant and reliable to accepted methods, common methods in the market. We allow a high accuracy due to the potential turbidity compensation. When this data is then collected, we are very flexible how we send this data to a higher layer SCADA or PLC system with the known field bus outputs or milliamps or whatever. And the sensors are of robust material, which ensure a high and long lifetime. So to summarize all this, one last slide on how to find the right wavelength at all. Because that was a question which received us at the very beginning before that, that meeting here. How can I choose which wavelength is the correct one? First of all, check the local regulations. Is there a regulation in your area which gives you the most common wavelength? Or if not, which wavelength is the customer using currently? Is he already doing lab or any kind of reference measurements? So you can use a wavelength linked to that lab measurement, because that makes the lab and the online monitoring comparable. By this, select this required wavelength in our sensor. Use the turbidity compensation, the true color measurement with a factor to see, do we need to compensate and how much we need to compensate that we fit to the lab value the best we can. Maybe use that second parameter for a better comparison, one with compensation, one without. And that sensor which fits best is then, the parameter and the wavelength to move on. Because that, I think, is one of the standard approaches worldwide, that the lab method is the reference for the customer and that online monitoring needs to fit to the lab. That is of highly interest in most customer cases. Yeah, so thanks again from my side again for listening and for taking the time. We do now have a few minutes left for questions and answers if there are any.